my talk, I was trying to show how the periodic table had influenced the evolution of organisms, particularly in the ocean. And I guess I was trying to show how availability of those elements has changed through geological history, primarily through the oxygenation or the oxidation of the ocean atmosphere system by the process of photosynthesis. And so we have good geological records in mass-independent isotopes of sulfur that show a big step in oxygen at about 2.2 billion years ago. And then we have good evidence, in fact, from changing trace elements in the ocean, that there was potentially a later additional step in oxidation between maybe 500 to 400 million years ago. And the interesting thing is, if we chart the dominant life in the ocean at these distinctive periods, and we look at the chemistry of that life, then it changes as you go from the cyanobacterial world into the eukaryotic world, where the elements that change, things like iron, become less available in the environment, and we see that the eukaryotes require less iron, but they require more copper and zinc, which increased in availability in the environment as that oxygen rose. And so we have this link between the changing elements in the ocean through this first oxygenation step in the ocean and the chemistry of the cyanobacteria going to the eukaryotes. And then there's even a further step in the dominant organisms in the ocean, around 200 million years ago, where we see the ocean changing from being dominated by the green algae to dominated by the red algae. And yet again, we see a change in the trace elements that's encoded by the genes for these organisms. And by and large, for almost every element, they require less of those metals than the green algae that were prevailing in the ocean before. And so my interpretation at the moment is that there's, again, a change in the chemistry of the ocean about 200 million years ago, associated with the deepening of the oxygen minimum zone. And that changes both the oxygenation of the surface ocean as well as the pH of the ocean. The pH goes up, and indeed this is the time that we see the advent of calcareous phytoplankton in the ocean. But that pH also changes the partitioning of trace elements onto iron oxyhydroxides. It speeds up the kinetics of formation and increases the adsorption of things like copper, zinc, manganese, are all precipitated out very much more rapidly or scavenged out of that water column. And the red algae, the red lineage algae, these secondary endosymbionts, adapt to this by reducing their metal requirements. And indeed, we see that they change to much lower requirements of all of these trace elements at that time. And that is potentially what allows them to prevail out into the main ocean, as well as building skeletons of calcium carbonate. And we've been looking at the proteome for things like transporters, and the key element, iron, appears to be one of the main drivers of this evolution. We get vanishingly low levels of iron. So at the same time as the organisms are minimizing their requirement to live, they're also having to work harder, and we see increases in the number of transporters they're dedicating to get iron into the cells at this time. So iron really seems to be the main limiting nutrient in the ocean today, and this is what has led to this idea of the iron hypothesis, that should we put additional iron into the ocean, we can fertilize photosynthesis, and actually that can draw carbon dioxide into the ocean, and potentially we have evidence that this has occurred during things like the ice ages, with dust supplying iron to the surface ocean. So I was trying to spin this tale of changing element availability, how we see that playing out in the dominant life forms in the ocean, and how that has actually driven climate and atmospheric composition over geological timescales.